Hello, guys. I want to give you a chance to catch up and see what you missed in class when we talked about confidence intervals. So, to start from the bottom, a confidence interval gives us an interval of plausible values for a parameter based on sample data. So, that means that, like for this example, if we had a huge container with different colored beads and we wanted to know the proportion that are red, that is the parameter P, is the proportion in the large container that are red. And we don't know that because it's a large container. We can estimate, but we don't know how much are really in there. So all we can do is take a sample, right? And we find P hat. And P hat has been our sample proportion. And they tell us that in that sample, sample size N of 251 beads, 107 were red. So that becomes what we call the point estimate or the sample statistic. And that number becomes the center of our interval. And we add plus or minus what's called the margin of error. And what that does is it creates an interval, and that is kind of like our best guess of what P could be, because we don't know what P is, but we do know P hat and we do know N. So we can kind of create this interval that way. So how does it all work? How do we actually create the interval? That's what we worked on these 3 days. So we have a template for interpreting the confidence interval. And we went through some of these slides together, if you remember. We learned that if you want to be more confident that your interval captures the true P, then you have to be willing to increase your margin of error. So you can see right here that when the percent confidence is higher, the interval actually gets bigger, which is kind of a bad thing because we want our interval to be nice and tight so we have a better idea of where the plausible values of P are. We looked at some examples together, and then we moved on and talked about confidence level as well, which we also have a template for that, which is right here. That's when it says like 95% confidence. What does that mean? Well, if we made a bunch of confidence intervals that were at the 95%, we would expect 95% of those to capture the true P. And of course, you'd provide some context. So here's all of those intervals, right? And then we had one that did not capture the true mean in this case. And that gives you a sense of percentage. So the percentage that are black, that's the confidence level. And we moved on. And we talked about some ways to make the margin of error smaller is to decrease your confidence level, which is kind of a bad thing because we'd like to be confident in our interval, but it will make the interval tighter if we decrease our confidence, or you can increase your sample size, which is costly because you have to ask more people, but that'll make your interval tighter too because it shrinks that variability. So there also was an activity we did around class. We actually had a beach ball that was the shape of a globe. It had all the water on it and all of the land. And what we did is we tossed around the ball and we kept track of whether everyone's left pointer finger was on land or was on water. And we found that when we did it 50 times, 50 catches, 32 times we were on water. So we wanted to investigate just that overall question: what proportion of Earth is covered by water? So we got 64% as our sample statistic, P hat, the sample proportion. And we could stop there and just say, hey, 64%. But if we were really trying to capture the proportion P, that's not a good enough answer. That's why confidence intervals exist. So we wanted to construct a 95% confidence interval to estimate the proportion of Earth that's water. So this right here is our 4C method. Choose, check, calculate, and conclude. So first, And this will be true all the way up to the first test that we'll have in class. The one sample Z interval for P. Interval just means confidence interval. Z is going to be part of the way we construct it. And one sample just means that that the population is just one group of people, or in this case, one group of locations. You have to state the confidence interval, and you have to talk about P and give context. Conditions. There are conditions to check, and we'll go over those in just a moment, but it's random, 10%, and normal. These two come from chapter 7. They're the same, except now we have to use P hat because we don't know P. We're trying to estimate P. So we checked out there. Those were bigger than 10. So the sampling distribution of P hat is approximately normal. We can use the standard deviation equation, right? Sampling without replacement is okay. And then the randomness means that we can generalize to all locations and it's scalable. So we make sure we quote random sample from the problem. And then we do the calculations. So this is the formula for a confidence interval for P. Okay, so this Z star is something that we haven't talked a lot about, but Z star is the number of standard deviations you need to go out to accommodate and capture the interval. Okay, so it controls the size of this number, right? In blue, this is just basically the standard deviation of P hat. It's not exactly because it's supposed to have P in here, if you remember from chapter 7, but we don't have P. So we have to kind of estimate it. So it's called the standard error, but it's basically the standard deviation still. So Z star is just how many of those standard deviations you want, times however big your standard deviation is. So for 95% confidence, it just so happens that it's about 2 standard deviations, which should make sense. That's the empirical rule from chapter 2. So it's just a way of constructing the interval. That's the number of standard deviations you want to go out, and this is the size of that standard deviation. So that's the margin of error. Okay, that's how all the formulas for confidence intervals are created. So we did get an interval out of this, and then we had to interpret it as our last part of the 4C method. And this stuff we'll get to in just a moment in the slides. But to conclude, we said, hey, we are 95% confident that the interval from blank to blank captures the true proportion of Earth's locations that are water. So we did a pretty good job. I mean, we got a pretty good interval of what percent of Earth is water, our best guess based on this sample. But if we did it again, maybe only 33 or maybe 30 or maybe 27 of our catches were on water, and it would be different, right? But if we did many, many of those, 95% of them would be successful in capturing the true proportion. And finally, briefly, I just want to go over some of the A2 notes that we covered in class. So this is just diving more into the logistics of a confidence interval for P. Here's the precise equation. It tells you exactly what Z star is. We really need normality though, and this is P. So large counts, right? This thing and this thing here, checking these two is going to be huge. And because we don't know P, it's going to be P hat, but we need to prove normality in order to use this Z star idea. It's called a critical value. Again, I already talked about it. It's the number of standard deviations that you choose to go out to get that level of confidence. So this stuff's provided on the formula sheet in different locations, but it's not tied up for you in the complete form that you'll need to know it for. It gives you the general template, but then you have to stick the stuff in the right spots. So you're going to have to put standard error in here. You're going to have to know that this is Z star, and you're going to have to know that the statistic is P hat. So it might just be easier if you just kind of knew this formula kind of by memory. Now, just with the way that we did things in chapter 7, there are conditions for confidence intervals as well. There's 3. One is the random condition, making sure that we have a random sample. With no random sample, we can't extend our thinking to the population at hand. Next, the large counts condition. That's checking that normality so that we can calculate Z star. Remember, we do use P hat. I'll talk more. We're going to do an example in just a minute on how to do find Z star. And finally, the 10% condition, if you remember, is checking this. And it allows us to make sure that the standard deviation formula is valid and that we can be okay even though we're sampling without replacement, right? Because we're when normally it's a survey, right, and a proportion of people who feel a certain way about something, maybe about their attitude towards certain legislation or something. Sampling it without replacement is a reality, right? When we sample someone, we don't sample them again. We pull them out and we don't replace them. So by checking this condition, we make sure that we can overlook that and continue with the problem. Okay. So here's just another slide for where the parts of the formula are. Here's the conditions again. Here's an example. Those beads. But with the conditions. Okay. Everything's written out here. This will get you the full points for the check part of the method, the 4C method, 4-part method. So yeah, let's say, for example, you have a 90% confidence interval and you have to find Z star. How do you do it? Well, it should be a Z. You set up a normal curve centered at 0, and you go out a certain amount. We don't know how far to go out, how many standard deviations to go out, but we know we want to capture that 90%. So we put 0.9 here, and then we take 0.9, we subtract it from 1, and divide by 2. So what that's doing is it's finding this little area right here, because it's the excess, but cut in half, because there's 2 tails. That amount is 5%. And so is this too, if you want to write it there too. So if we want to find this tick mark right here, negative Z star, we know the area. And remember, if we know area on a normal curve, we can use inverse norm to use that left area, the mean and the standard deviation, and we can get our calculator to give us the tick mark, which in this case is negative 1.645. I can divide both sides by negative 1 and get this. So this is just what I plop into my formula, and it works out. So, because remember, our confidence level has a direct impact on what the interval looks like, specifically the margin of error. So remember, it all boils down to this equation. And when we calculate this, again, it's allowing us to calculate how far do you want to go out, right? So this 1.6, that's actually kind of small for the confidence or for the Z stars that we see. If we get to like 99%, Z star can get a little bit bigger, like bigger than 2, closer to 3. But that makes sense because when you increase the confidence level, you have to increase the margin of error. As you saw in the slides kind of towards the beginning of these videos, this could be a 90% interval, nice and tight, but the 99% is better because it's 99% confident. And if we did multiple intervals, we would hit more often. But the negative is a wider interval, and it's not really good in terms of like practicality. Like that's not really like helping us estimate that much if it's like so wide. So that's what Z star does. It's directly related to C, like that confidence level. It doesn't matter what N is or anything like that. It's just its own thing, and it goes with the confidence interval. So the AP exam and just real life, we normally use these 3 confidence levels. Very rarely do we see something other than it. So therefore, it could be kind of to your advantage to have these memorized. So this one goes with the 95%, and you can see the picture drawn there. You could do inverse norm and find this number that way. Okay. Again, the 4C method for confidence intervals, this is our main way. This is how we do FRQs when they ask you to find a confidence interval. We have a whole packet that I created to do this. So the last thing I'm going to do here in these videos, very last thing, I want to walk through one example with you. I'm actually not going to write anything. We're just going to look at the slides, and it's going to go through the 4-step process again. So I showed it to you with that globe example where we did the water. But here's one more example just so you can kind of see at a glance, what are confidence intervals? What are they doing? What am I going to be expected to complete? Because you'll have an FRQ on a test asking to do the 4-step process, the 4C process. Okay, so we have a bunch of cell phone users. This is N, the sample size. And we found that 170 of them admit to walking into someone when they're on their phone. Okay, here's our confidence level for the proportion of all cell phone users who admit to walking into someone. That is P, that proportion. Okay. P hat is going to be the number of, quote, successes over the sample size. Okay. So we have N and P hat, and we know that C, the confidence level, is 95%. So that's kind of what we pull. And it's asking us to make a confidence interval. So the first C is choose. You must say this verbatim. They are very particular on the words you pick. So you must say one sample Z interval for P. Okay? You have to mention the confidence level for that interval. And then you have to give some context of P. You must say P and the true proportion of your context. So in this case, all those people that are running into someone when they're on their phone. Conditions, that's the second C, check. So we see that they say random sample. They check the 10% condition. The randomness is good. 10% is good because of this being reasonable. And then they check large counts because that's normality. I actually normally say normal here. And then I check this is a P problem. So you have to use the large counts, not CLT. That's for means. Okay. And then the calculate step. So they actually don't grade any of this except for the answer. So the way you get to it is kind of up to you. but a good template is to do 3 steps. Write the general formula, write the specific formula, which there's 4 specific formulas that we're going to study. And this is the one for P, single P. Okay, you plug in the numbers. So notice that they plugged in Z star for the 95%. And this was on the table I showed you earlier. Okay, and then they plugged in P hat and then plugged in N. So part of this calculate, you might actually have to make that 95% and do the Z star thing and do that out. But hopefully you just know that Z star is 1.96 for 95%. That table is important, and we're kind of banking on knowing that. But if you don't, you can find it manually. And then conclude is the last C. Okay? So it's our exact template. We're 95% confident, blank to blank, captures the true P. Right? So they're about like 23%, give or take. Sure. Right? They're 95% sure, confident, that interval will do a good job of capturing the true P. But who knows? It might not, because we did a sample, and that sample, who knows, due to random chance, it could have just been a bunch of people who were really clumsy, and we might not capture P, but we're 95% sure. So if we made a bunch of intervals, 95% of them would capture P. So that's kind of where we're at, okay? And this will catch you up, all right? And we'll get you that packet that we started, and which has got a lot of problems on it, a lot of good problems. It starts with the volleyball problem, and we'll get you caught up, all right?